Take two.
Okay, again, back into chapter 10. Let's begin at chapter 10.1. Right triangle trigonometry. Right triangle trigonometry. So we're going to be dealing with triangles that have a 90-degree angle within it. Okay, a 90-degree angle, that's what we're going to be focusing on at first. What's interesting about this is no matter how you flip-flop this triangle, this will work in any direction, and we're going to see how it can work a little bit later on as we implement that with the Cartesian plane. So again, have a piece of paper out, begin to write these definitions, because committing them from your brain, hearing them, and then actually writing them down is going to help you a lot, especially by creating some sort of reference sheet. Because you have references all throughout your book, but they're all on different pages. If you can put all of these things on one page, it's going to be really, really useful. So let's begin by looking at some of the first definitions, and you should be familiar with at least these words or terms. You may not remember what they are, but we'll go over them, and that'll be fine. Also with this, have some sort of calculator, whether it's a scientific calculator. If you happen to have a smartphone or tablet that has a calculator app on it, then we can use it as well. In fact, just to kind of show you that, this is my phone. If you open up your calculator app, you will see regular calculator just like this, okay? But if you turn it sideways, most of them will turn it into a scientific calculator. The application is free. It does a lot of what the lower end scientific calculators will do, and this will be enough for this class by using it. You can use a scientific calculator. Those actually will do a little bit more, especially for whenever we input formulas in, but that's a little bit later on. Notice, if y'all would, because this is extremely important, you will see an RAD button, okay? And you should see where it says RAD somewhere on the display screen. That is typically what we use whenever we are doing calculations, okay? This is called radians. We're going to go over what radians are here after a while. If you happen to see on your iPhone, whenever you push the RAD is up, and then the button turned to DEG. The RAD button should have turned to DEG. Now on your scientific calculators, you will most likely have a button that says RAD and DEG. RAD stands for radian, that's your standard calculation. DEG stands for degrees. So we're going to be using functions like sine, cosine, tangents, secant, cosecant, cotangents. Whenever we start using that, we need it in the degree form in order for our calculations to be accurate. Otherwise, you're going to come up with these other numbers that don't make sense. Okay? So for right now, turn everything to where you see the DEG at the top of your screen, or on your display screen. DEG. If it's not on your display screen, then your RAD probably went away. Okay? Everybody have a screen like this?
Yes.
Okay. Down at the bottom left,
Yeah.
it will say DEG. And on your display screen, it says RAD. Right?
Yeah.
Hit DEG. The RAD in the display goes away. So now you're in degree mode. Okay? Cool. So we're going to be referencing this here after a while. Another portion of this book that we're going to be using is on page 612. Everybody turn to page 612. Turn to page 612. And there is a table of trigonometric ratios. And it goes all the way to 617. Okay? We will be using this a lot as well, so be familiar with this. 612 through 617. This will be your friend because this is a quick reference that you can use. You can use your calculator or you can use this reference page. Now, let's go over how to use this reference page first. You first have if you look on the far left side, page 612, you're going to see degrees. And you have 0 degrees and then 0, 0 and a hash mark at the top right of it. Okay, that means minutes. So if you think of a clock, there are 60 minutes in 1 hour. So kind of think of that degree, the whole degree as being 1 hour. And then the part next to it is going to be minutes. Okay? So you could take the minutes portion and be able to determine what fraction of an entire minute it is, okay, or an entire degree. Now, you also have a reference to radians there, okay, so if you have things in radians and you need to switch it from degree to radians, then you can reference that and do that. Then if you look across, then you have sine, cosine, tangent, cotangent, secant, and cosecant. So what you could do is, if it says, what is the tangent of 1 degree? Well, everybody go to 1 degree, and then slide your finger all the way across until you're in that list of numbers underneath TAN for tangent, and you will see 0.0175. Okay? Now, what happens is as you go down that list and you keep turning the page and you go all the way to 617, it ends, the very last one on the left-hand side is 45 degrees. 45 degrees. Now what I want you to do is slide all the way across to the other side of that table. You will see 45 degrees. If you start going up, you see it climbing. And go backward into this table now to page 616. Along the right side, it keeps climbing in degrees, 47, 48, 49, 50, and so on. To where if you end up going to the very first page, your last one is 90 degrees. Okay, so basically what's happening is as you go across this table here, and you have all these numbers, you can go down this way and the degrees increase as you go page by page, and then your last page is going to end at 45. Well, then 45, you can continue all the way up here. This starts at 0. Your last will be 90 degrees. So you keep going up this way. Now, if you are on the left side of this page and you're looking for sine, cosine, or so on, you read across that way. If you're coming up this way, then you will read from the bottom, going up. Does that make sense? Because that can be kind of confusing for some people. So, if you needed to find, and notice down at the bottom, here you have sine, cosine, tangent, and so on written at the top. You also have those same ones down at the bottom where it says cosine, sine, tangent, and so on down at the bottom. So if you are reading the right side of the page, you need to follow the column for the words at the bottom. Does that make sense? Is everybody clear on that? So if you're following the degrees on the left side, you go to the column as it's listed up top. If you're looking at the degrees on the right side of the page, you follow the column for the terms as they're listed on the bottom. Follow it up and then find out what that measurement is. Okay?
So question.
Yes?
Will we have to do it a certain way, or is that for us to decide which way we do it?
There's only one way to do it. Otherwise, you'll end up with an incorrect answer. So if I said find 47 degrees, okay, we'll do the tangent of 47, I'm sorry, let's do 69 degrees. What is the tangent of 69 degrees? So you should find 69 degrees on page 614.
214.65.
Yes. So you'll see 69 degrees on the right side of the page. You'll look for tangent on the bottom since you're on the right side of the page and follow it up until you come to 69 degrees and you'll see 2.605. And that's how you will find that. Notice what's interesting is that is also the cotangent for 21 degrees. So you will see how these relate to each other, and we'll get into that in a little bit. We're kind of jumping ahead just for the sake of understanding this table, but we'll go back and you'll understand what each term means and what is actually taking place. Okay? Does everybody understand the table? Please shake your head side to side if you do not. Okay, cool. We'll have plenty of opportunity to work on this and actually use it. So, what we're going to start off with are sines, cosines, and tangents. Okay, and I want to look at page 394 and 395 at the same time, because we have our definitions on 394, but then we have a table reference that helps us on 395 to kind of give a little bit more visual of what's going on. So, first of all, who remembers sine, cosine, and tangent from earlier courses? Okay, so does anybody remember what sine is? How do you calculate sine in a right triangle? Do you remember? Let me ask you this. What is, we have a right triangle. And we are told it's a right triangle because it is marked this way. Even though my drawing is not accurate, we can understand that this is a right triangle because of this box here. This means this is 90 degrees. Okay? Now, whenever we are trying to find the sine of, say, this angle, and we can say A, B, C, and these are labeling the sides with angles. We'll go into the angles here in just a little bit, but if we're trying to figure out this angle, then there is a way to figure it out if we understand the lengths of the sides. First of all, does anybody remember what the side C is called? There is a common name for that. The hypotenuse. Very good. Hypotenuse. So anytime you see hypotenuse, it is the side that is opposite the 90-degree angle. Now, whenever we're doing sine, S-I-N, that is going to equal the calculation of the opposite side over the hypotenuse. So if we knew that side A was 9 and side C was 14, well then we can say the sine is going to be 9 over 14. Sine of angle A. Okay? Angle B, and then this would be angle C. So the sine, now how we would actually write this is sine of A, capital A meaning an angle, and then that's going to be opposite over hypotenuse. Now, if we're going to look for cosine, cosine of A is going to equal adjacent over hypotenuse. Adjacent is that side that actually connects to that angle you're looking at. Not the hypotenuse, but that side that it actually connects to the angle that you're talking about. Adjacent over hypotenuse. Okay, and then somebody tell me what tangent is. Look at your book, and what would tangent of angle A be? Or tangent of any angle?
Opposite over adjacent.
Very good. Opposite over adjacent. So cosine is going to be B over C. The tangent is going to be A, side A over side B. So here we can calculate that. Now, what if we were simply given this angle, angle 27? Okay, this is a 27-degree angle. What is the sine of angle 27? this is all you're given. Okay, in fact, you don't even know these values. This is all you're given. What is the sine of angle 27? Well, we know that it is the sine of 27 degrees is A over C, but what's that value? Somebody tell me. You can do whatever you want to figure it out, I don't care. Anything you want. I just need a correct answer, that's all. Just one and only one correct answer. Still waiting. One person is sheepishly correctly finding out this answer, but it's almost like they're in trouble for doing it. It's kind of funny. So they're
0.454.
Yes, thank you. Awesome. So
because nobody else is doing it, so
exactly.
I'm like,
What is wrong?
Flipping through my book.
Exactly. That's only very good. Now the light bulbs start going. Wait, that's right. We were just talking about that table thingy. And so yes, you can turn back to page 6. Is it on
612,
15, right?
12, 6, 12,
This
3,
one's
6,
on
17.
what page was it on?
615.
615. Okay. 615. Go to angle 27 and look under sine, and it's 0.4540. That is the sine of angle 27. So there you have it. So now we found out 2 different ways of doing this. Now to go into your calculators, everybody open up your calculator, turn it sideways so that you have it in scientific mode, or use your, yes, you can, turning your scientific calculator sideways doesn't make it more scientific. So it's just going to be a little bit harder to read. So again, make sure that that RAD is not visible up there. We're going to be using degrees, and we can type in 27 and then hit sine. Okay, now you'll see it a little bit slightly different than what the book is because the book rounds. So here on your calculator you'll see 0.453990. It rounds it up to 0.4540 in your book. Okay, close enough.
You said you want it in rad and
No, you want it in degrees.
okay.
If it's in radians, then it's going to be incorrect information.
Yeah.
Okay, so 3 different ways that we can do this. 1, if we're given enough information about the sides, then we know how to calculate that. If we're simply given a degree, then we can go to our table, find the degree, and determine and find out what specific amount we're looking for depending on what it's asking us, whether it's sine, cosine, tangent, whatever. Or we can use our calculator and plug it in that way. All right? Cool. So, again, just to go over this, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, everybody got that? So, in looking at example number 1, we have angles S, T, and U, and it's asking us to give the exact value of the 3 basic trigonometric ratios for the 2 acute angles in the triangle shown here. Okay, so here we are going to use what we have, or what we just discussed. We are given pieces of information and then we can go on from there to start actually answering those questions. whenever you have a problem that has 3 bits of information and you have 2 bits of that information, you can find the third. Okay, and this is a perfect example of doing that. So we have this triangle here, right triangle, and we are given 3 and 7. 3 is the length of this bottom side, 7 for this upright side. We do not know what the hypotenuse is. And it's labeled S, T, and U. Now, who of you remember how to find the length of the hypotenuse?
A to the second plus B to the second equals C.
Yes, very good. Do you remember what it's called?
Something theorem.
What's that?
Something theorem, right?
Yes.
The Pythagorean.
Pythagorean.
Keep going. Pythagorean theorem. Pythagorean theorem? Yes.
Yeah.
Pythagorean theorem. So, yes, it is a squared plus b squared equals c squared. Very, very important to remember. Okay. Now, it really does not matter what a and b, which sides a and b are, as long as c is the hypotenuse. So basically, you're squaring one side, adding it to the square of the other side, and that will equal the square of the hypotenuse in a right triangle. In a right triangle. So here, we will be doing 3 squared plus 7 squared, and that's going to equal c squared, which gives us 9 plus 49 equals c squared. So that gives us 58 equals c squared. Now, what is the opposite or inverse operation of c squared?
Square root.
Square root, perfect. So we take the square root of both sides. I'm going to move this over here to make it bigger. So we take the square roots of both sides. This square root cancels out that square, so we have c equals the square root of 58. So c, side c equals the square root of 58. Now, why did we have to go through all of this? Because the hypotenuse is what's used in our ratios to find sine and cosine. We don't need it for tangent. If it asks for tangent, then we don't need it because we already had these two, opposite over adjacent. So let me ask you this. If we were looking for this angle, what would be the tangent? Give me the ratio for tangent. It'd be what over what?
Opposite over adjacent.
Okay, so what number over what number?
A would be, so that would be square root of 58 over 3.
Close? Well, not quite, because this is going to be the hypotenuse.
C. So
Okay.
it would be 3 over 7.
3 over 7, very good. So the tangent of S is going to equal 3 over 7. Okay? Likewise, the tangent of T is actually going to be 7 over 3, the opposite over the adjacent side. So tangent, again, we don't need the hypotenuse. If we're going to be looking for sine and cosine, we have to have that hypotenuse to be able to do the other part of the equation. So you may have to fill in some of these blanks first in order to get where you need to go. All good? Yes, sweet. Now, if you look on page 396, or example 2 in 10.1, it'll say find the following ratios. So it says sine of 58 degrees. So then you can go to your table and find 58 degrees. It says a tangent of 27 degrees in 40 minutes. Go to 27, and you'll see between 27 and 28, that it varies in degrees, 10, 20, 30, 40, and so on. So now notice it stops at 50. Why is that? So to make sure everybody understands the question, if let's say we look at 27 degrees and then you see 28 degrees, well, in between them you have 10, 20, 30, 40, 50, and then 28 begins. Why is that? Yes, very good, because there's 60 minutes in 1 hour, 60 minutes in 1 degree. So once you hit 60, well, just like it would be a new hour, or the next hour, it is now the next whole degree. So that's why that's happening. Okay, so if you think in terms of 60. Now remember that, because whenever we deal with radians, then we're also going to be talking kind of in terms of rotations, or 60-degree turn, or 60 degrees and other degrees, but going around in circles, okay, like you would a clock. So just keep that part in the back of your mind. All right, let's move along to 10.2. 10.2. Now that we know several different ways of how to find this information, now we can go from just basic, what is the sign of this, we can actually start problem solving a little bit more. So here, we're going to be doing some problem solving, and if you look at the, I'll read this briefly and then we'll go in how it's used a little bit more here in a little bit. But in the paragraph up top it says, finding an angle for a given value of the sine is called the inverse sine, or arc sine. This is symbolized by sine to the power of -1. Okay? Or you may see arc sine. Some calculators have that on there. Not all of the application calculators will have those, but your scientific calculators most likely do. So let's do this. Just understanding that, and again, kind of putting in the back of your mind where at times, if you look at example number 1, you'll see sine of some degree is 4/7. So basically what we're saying is we have, or what this question is saying is we have a right triangle. We have 4 and 7. We are looking for this angle x here. Okay, because the sine is opposite over hypotenuse. What is the measure of this angle here? Well, then what happens is whenever we're essentially dividing by a sine, x is going to equal the arc sine of 4/7. Now another way to understand this, because if you think about it, if you do the inverse operation, you can have 4/7 divided by sine. Or it's actually 4/7 times 1/sine. Okay? So 1 over sine will end up being the arc sine. Okay? So if you don't have an arc sine option, you can still calculate information given what you have here. And we're going to go through some examples on how to do that. Okay? But it's good to understand this concept first so you know what you're doing. This is just like using this as a number. If this was 5, well, you divide 4/7 divided by 5. Okay? In order to figure out what x is. Well, now since we're talking about determining angles, that's where we're going to be, and as they refer to right triangles, then we can take that information and still figure out certain aspects of this. So let's do this first, let's go to let's go to page 400. Okay, first what we're going to look at are these definitions, and then we're going to skip to example 3. First of all, first definition, angle of elevation. Okay, the angle formed by a horizontal line and the line of sight toward an object that is above the horizontal. So if you look at that little fellow there with the cool little hat, and he's standing there and he's looking at a watchtower and a person at the top of the tower. Well, the line of sight, okay, is going directly toward the object. If I were to look at this wall, and then the angle of elevation would be if I'm looking up to the ceiling from this position. On the diagram, the sight, or the horizontal line, or the line of sight goes directly toward the object, okay, that is in front of him, but the line of sight, the horizontal is whenever you're facing directly at the object. The line of sight is the angle at which they are looking up to whatever designated point of that object. Here he's looking at the person on top of the watchtower. The angle of depression is the angle formed by a horizontal line and the line of sight toward an object that is below the horizontal. Okay, so angle of elevation and angle of depression. Angle of elevation is somebody who's basically on the ground and they're looking up, compared to looking straight across. So you have your horizontal and then that angle that is actually going up, looking up to something. The angle of depression is if you were up high, you would look straight across horizontally, and then the angle that you're looking down to an object is going to be the angle of depression. Okay? Does that make sense? Easy enough? Cool. So, understanding that, let's look at example 3. An engineer sets up a transit survey instrument in a convenient spot and measures the distance to the base of a building to be 75 feet. Okay, if the angle of elevation of the top of the building measures 67 degrees, find the height of the building. Okay, so this guy has what's called a transit at this building here. Okay, just some building. You have a tripod, it has this thing, and from here to here is 75 feet. And then the line of sight is a horizontal line from this instrument. He's looking through, these things are used for all sorts of different things, whether you're going to build buildings or you're going to be building roadways or you need to map certain structures. This is basically like a lens or camera. So he's going to look through there and it's going to go straight across. And then he's also looking up to the very top of this building. So we have a distance. We know that this side is 75 feet because from here to here is 75 feet wide. This angle is 67 degrees. Okay? So, now what we have is, now what it's asking for is this distance here. Okay, what is the distance from here all the way up to the top? Well, we don't know this, which is the hypotenuse of the right triangle, which is extremely important in this. The reason why we're looking at a horizontal line, or we use a horizontal line, is because whenever we make a horizontal line to a flat object and then look up to the top of that same object, we're creating a 90-degree angle. Then this allows us to use these calculations. We don't know what this is. We do know what the angle is, and we know what one of these sides are. So what do you think we're going to use? Do you think we'll involve sine, cosine, or tangent in this? Without looking at the book. Well, which side are we trying to determine? Yeah, the hypotenuse, this one here. So we need to know what this is. We don't know what that is. We do know this length. This really isn't coming into play at all, and we're referencing this angle. So according to this angle, what do we have? Like, very good. We do have a triangle. That's very impressive. You should become an excavator and be able to get your digging tools out with triangles and stuff. So here, if you have an angle that is on either side of, sides that are directly involved with this, then would you use sine, cosine, or tangent, and why? Sine, cosine, tangent, and y.
Say tangent. You're trying to find that.
Okay. Using the tangent because we're trying to find the hypotenuse. Does that make sense?
No.
No. Well, you're right with tangent. Okay, but why is that?
It's opposite over adjacent.
Opposite over adjacent. Well, would this be opposite over adjacent?
Yes.
Okay, go ahead.
I was doing hand motions to follow what I was thinking, but yeah.
Okay.
I just,
Talk to
yeah.
So let's do this. What if... Now, let me ask you this. Why does this not make sense?
What?
Why does it not make sense? You're saying tangent. Probably saying tangent because that's what the book tells you to do.
No.
No? Really? Okay,
Because
well...
I'm going to go on a tangent if I don't get it.
Yeah.
Okay, there you go. Now, so everybody read through your problem. Okay? And what is wrong with what we are looking at here? Go ahead.
We're trying to height this building.
Very good. Yes, we are trying to find the height of the building, not the hypotenuse, not the distance that you're looking from. We are actually trying to find this distance right here. Okay? Which goes to show it is very, very necessary that you read the problem carefully. Don't take any information for granted, but make sure that you know what the problem says and what it's asking you to do. Otherwise, you end up going off in the wrong direction. We don't need this. We need this here. Now, given that we have this angle and this side, why is tangent the correct one to use?
Opposite over adjacent.
Right. Opposite over adjacent will give us that. Otherwise, if this were here, which one would we be using?
I don't
Well, there's two other possible ones out of three. Would it be sine? Would it be
It
sine?
would be the B over C, which is the
Cosine.
cosine.
Yes. So it's adjacent over the hypotenuse would be cosine. Okay, so very, very good. So what we're looking for is the height of this building. Okay? Now, one thing that we're going to pay attention to with information we'll address in a little bit, but this x is not the only information that we're going to have to consider. But this is a large piece, a missing piece of this puzzle that's necessary. All right, so we're going to do tangent of 67 degrees equals Opposite over hypotenuse, x over 75. Okay, so how do we determine x? How do we calculate x? First of all, it's easier if we have the tangent of a degree. Let's go ahead and find out what that is. So whichever way you want to use it, you can either use your book or you can use your calculator. Let's find what that value is. What is tangent of 67?
0.269. 0.2679, sorry. 75. Oh, 67.
67.
2.356.
Very good. 2.356. So if you use your calculator, you would have had 2.355852365, whatever. If you used your book, then you should have been on the right side of that page and found 67, gone down to read the bottom tangent, and gone up from there to find 2.356. So now we have 2.356 equals x over 75. Now how do we get x by itself?
Times 75.
Times 75. We do the inverse operation. Here we're dividing by 75. So now we need to multiply by 75 on both sides. Okay?
176.7.
176.7 equals x. All right? Very good. Are we done?
No.
Do we know the height of the building?
No.
Why? What are we missing?
We have to
Add
add
the
that.
5.
Very, very good. Very good. The information in the problem tells us that the instrument here is actually set up 5 feet off the ground, or this portion that gives us the horizontal line is actually 5 feet from the ground. So we have to take 176.7 plus 5, which is going to get us 181.7. And that is the height of this building total. Very good. So we not only got to learn a little bit about trigonometry, but also some more into word problems and making sure we're paying attention and actually answering the right question. Otherwise, we get things all sorts of jacked up.
Understood. Understand.
Are there any questions with this so far? Does this seem massively confusing?
No, it's so nice that it's easy.
It's actually really, really not difficult. But don't get too excited because it does get harder. Yay for hard math. You know why this isn't difficult? Because we broke it down into pieces that we know we can do. So we started off with just this information, and we make our drawing and we plug in what we know and what we don't know. Here, if you saw, tell me tangent of 67 degrees equals x over 75 before you walked into class today, would you be able to do it? You'd be like, I think I'm in the wrong class, I'm sorry. But no, here we're like, oh, I can figure out this part, tangent of 67 degrees, I know how to do that. So then we end up with this. Oh, well, we've done this a lot, where we have this, and all we're simply trying to do is get x by itself. So then we're taking in some of what we've already learned, and we found out the actual value. We've done word problems. We read our word problems completely, and we found that once we found this answer, we are not done, because there's more to it. Add it in, and now we get that answer correct. If you were to take the PSAT or SAT, and you would most likely have something like this on that test, I guarantee you this is going to be one of your answers. And you're like, oh, I got that. Yeah, that's one of them. And you mark it, and it's wrong. Because you did not account that 5 extra feet. So a lot of those tests will incorporate those common mistakes that people make. That's what I'm trying to say. Commonly common. Uncommonly common than for more common people.
I understand it.
Yes. All right. So now we have something. Let's look at example 4. let's look at example 4. This is going to be very similar, but from a different perspective. Okay, you can still apply the same concepts from more than one perspective, meaning looking at it at a different way. So Jeff wants to know the approximate distance across a certain part of a lake. That is going to be the same thing as the height of the building we were just looking at. We're starting at a point and we need to know the distance across this lake. So if you think about it, if you took the surface of the lake and put it upright, then we could do what we just did. But we're not going to do that. We're actually going to lay on our side on the ground and accomplish the same thing. Okay? So from the distance across a certain part of the lake from A to B, he measures a distance along the shore from A to C being 33 paces or 100 feet. He estimates angle C to be 80 degrees. Find the distance across the lake from A to B. So we have this. Here's our right triangle because he starts here. Okay, well, I'm sorry. He actually starts here and looks across. Okay, what would this end up being? What is this called? The angle of what? The first one was the angle of elevation because you're looking up above the horizontal. This one is going to be the angle of depression, very good, because you have your horizontal line and it's the angle in which you are looking down below the horizontal. So angle of depression. I bring this up because it may ask you in your homework what's the angle of elevation or what's the angle of depression. You need to understand what's going on. Angle of elevation is whenever you look across and then you're going to look up. Angle of depression is you're looking across and then you look down. Okay? So we know that because we're using angle of depression, we have a 90-degree angle here. This is 100 feet, and this is an 80 degree. Incidentally, let's see, not 80 squared, 80 degrees. Incidentally, what will this angle be?
20. Wait, no.
If we know that this is a right angle, this is 80 degrees, what is this angle?
60.
What do y'all think? How many degrees are in a triangle? Total degrees are in a triangle. You said we were going to be talking about trigonometry, not like adding and stuff. That's kind of messed up. You tricked us there. 180 degrees total. So if here we have 90, that's 80. How much is left?
30.
Huh?
30, right? No, wait.
Another way to think about it is 180, you can have two 90-degree angles. One's 90. So basically your other two angles will add up to be 90 degrees.
10.
So 10. This will be a 10-degree angle. Which, depending on what's going on and what you're asked and what you're given, you may find it easier to find out certain information simply by using the 10 degree, even though you weren't given that. You were given 80. Well, I would rather use 10 because of these reasons. Know that that option is out there. So here, what we're going to do is we are looking for the distance of AB, between A and B. So, since we're looking for this distance, we have, and we're starting here, then the tangent, well, we're not starting here, we're actually going to use this. The 80, it's asking us to use the 80 degrees. So the tangent of 80 degrees equals x opposite over adjacent, and then we can go through the same method as we did before. If we ended up using the 10 degrees, and we could do tangent of 10 degrees equals 100 over x. Depends on what method you want to use. So, somebody tell me what is the value of tangent of 80 degrees? What is the tangent of 80 degrees?
5.67.
5.67. Anyone disagree? Can someone else confirm it?
Yes.
Okay. Now, what is the value of x? How do we figure that out?
Oh,
We
Wait.
multiply by 100.
Yep.
Both sides. So we multiply 5.67 by 102. And that gives us 567.
567. So, the length of this side is 567 feet.
it says rough.
Okay? What if I were to tell you that then the distance from C to B is 482? What would you think about that?
I'd take the shorter route.
Huh?
I'd take the shorter route to get to B.
Well, what about
Yeah.
482 being the distance from C to B?
Can't be right.
Why can't it be right?
Because from C to B is longer than A to B.
Okay. Visually, that looks correct. How do you know that that's correct? In a right triangle, what is side CB? What's it called? Hypotenuse.
Yeah.
Yes. The hypotenuse, that length or that side, is always longer than the other two sides, any one of the other two sides. It is always the longest side. So if you ended up, and it's asking you information, and you ended up with this, you know you did something wrong, because this cannot be accurate compared to this. The hypotenuse must be greater than 567 feet. Okay, so that's kind of a way to check your answers a little bit when dealing with right triangles. All right, good job, everybody. Good, good, good. Okay, let's go to 10.3, and we're going to look at special triangles. Because these types of triangles are triangles too. We got to treat them the same as everyone else, or as all the other triangles. We've been talking about right triangles, so now we're going to kind of delve into, yes, delve. You like that? Yeah, I know it is. It's a word, back off. So, got all defensive there. We'll have our 30, 60, okay, and 45 and 45. What's interesting is, what is 30 plus 60?
90.
90. Okay, so we have a 90-degree triangle, and one is 30, one is 60. The other one that we'll be using is, we have a right triangle, and we'll have 45 and 45 degrees, or gerdes, depends. Now, what's interesting is, whenever you calculate these ratios with regard to these, the ratio is going to be consistent. Okay? So, what we have is, when this is 1 and the hypotenuse is 2, this side is going to be the square root of 3. Likewise, on a 45, 45, we'll have 1, 1, and the square root of 2. Now, understanding this, if you were told that you had a 30-60 triangle, and so you have 30-60 triangle, and we'll keep it consistent right now, 30, and this is not visually correct, 60. And this was 3. What would the length of the hypotenuse be, you think?
Greater than 3.
Very good.
Wow, yeah.
But what would it be exactly?
Well, can we assume
the other one, the other side is 1. So it'll be the square root of 4.
Well, that's if you're assuming that. Let's look at here. We know that this is going to be consistent no matter what we do.
Oh.
So what would be the hypotenuse on this? If this is 3, what would the hypotenuse be? 6. So we're saying since when this is 1, this is 2, well, when this is 3, this one has to be 6, which means this would have to be what?
Square root of 6
The square root of
or 2. Or
9.
No.
it would be 2.
No.
7. 1.
3 times the square root of
Oh,
3?
Oh.
Because we're multiplying, if this is 3, we're essentially multiplying all pieces by 3. Okay? Now, let's test that theory and see if that's accurate or inaccurate, because that's what some people might consider. So let's check this out. Okay? We'll do this a couple of different ways. First, we'll do a squared plus b squared equals c squared. So we have 3 square root of 3 squared plus 3 squared equals 6 squared. So we have 9 times 3, which is, now the square root of 3 squared is what? Yes. And I mean that.
Say 3.
Yes. So basically it's 3 squared times 3, because the square root of 3 squared is 3. Plus 9 equals 36. Okay, and 3 squared is 9 times 3 is 27. Plus 9 equals 36, and that is true. 36 equals 36. So that is true. Now, somebody tell me what the sine of 30 is. What is the sine of 30? 30 degrees.
0.5.
What's that?
0.5.
0.5, 0.5. Okay, now let's do this given the information that we have here. The sine of 30 degrees equals opposite 3 over the hypotenuse, which is 6, which equals 1/2 or 0.5. So that's accurate as well. Okay, several different ways to confirm what we're talking about is actually true. So it is a ratio, and so as one is affected, it will affect the other measurements similarly to this setup here. So memorize this or have this where you can access it, because if you're given a 30-60 triangle and you're given one of the sides, you can determine the other two sides simply based on that ratio. And likewise with this one here. If you have a 45-degree angle, well, it's 1. When this is 1 and this is 1, well, these two have to be the same length if these are 45-degree angles. Then the hypotenuse will be the square root of 2. Okay? Likewise, if this was 5, then if this length is 5, this length would be 5, and the hypotenuse would be 5 times the square root of 2. Does that make sense, or does anybody not understand? Now's the time to ask questions. Cool. So, let's do this. We have a triangle, right triangle. This is a 30-degree angle here, 90 degrees, and this is 10. Fix that. Okay? Tell me what this side will be. It's going to be side x. Tell me what side x, that length of that leg will be.
It's gonna be 5.
Don't say it out loud. You're
Say
wrong.
5.
You're wrong, but
Is it always half of what's on the hypotenuse?
Maybe. Is it?
Well, I
What do
mean,
you
like
think?
because
If this were-
I know when we did the 6 and the 3,
Mhm.
it was half,
If
And
this
then
were
that's
20, what
half.
would this be?
10. So it's always half.
Yeah. Now tell me what this one is. What's y given that? And how are you figuring that out? Because there are actually a couple different ways you can do this. Don't blurt out the answer.
Sorry. I just couldn't contain this.
67! You have math Tourette's.
I do. Doing all this math now.
Yes.
Don't you have to do like the tan or like the sim or something? Find it?
There's a couple different ways. There's actually, there are 3 ways that we've gone over that can get you to determine the value of y, that length of that side. Do you already know? Think, think, think. All right, so let's do this. How did we get from 2 to 10? If we're using this as ratios, how would we get from 2 to 10? What did we do to the 2? Multiply times 5. Same thing with this one. We know that this is 5 because it's 1 times 5. The ratio, consistent ratio in this is multiplying by 5. So then you got to do the same thing to this. So it'd be 5 times the square root of 3. Another way you could do this is your Pythagorean theorem. We know that y squared plus 5 squared equals 10 squared. Okay, or y squared plus 25 equals 100, or y squared equals 75, y equals the square root of 75, which is 25 times 3. Square root of 25 times the square root of 3, which equals 5 times the square root of 3. That's another way. Another way that we've done already is, since we're looking for this and we're talking about the 30 degree, well then we can do the tangent of 30 degrees equals opposite over adjacent, so which equals 5 over y, and then we can go on from there. Okay? So we would figure out what this is, bring y over here, divide 5 by the tangent of 30 degrees, and we end up with 5 to the square root of 3. We'll end up with it that way. You could do the cosine of 30 degrees equals adjacent y over hypotenuse 10. And so find the cosine of 30 degrees, multiply it times 10, and you will get y.
I like that.
All these different ways, I know. And what's interesting is there are, I guarantee you, well, it would be odd if all of y'all said, this one way makes the most sense to me every single time I could get it right. Okay, some of y'all even though it may be a little bit more difficult, would say this makes more sense to me. Others, man, I like this, and I can even see visually ahead of time that y is going to end up on top, and I'm going to set that up. Or you may understand ratios really well and be able to do this in your head. All of these are correct. There is no one way that is more correct than another. It's what gets you there to the right answer that matters. Okay? Do each of these ways make sense on how we're getting there? Awesome. Good job, good job, good job. All right, let's do 10.4. I am going to go over this briefly. I only really want to talk about the concept of this. More so just for the concept and its use a little bit later on in the chapter. But not so much in this particular section. It's more identification than anything else. Now, whenever we've talked about the Cartesian plane, okay, and that's whenever we graphed information, typically some sort of either line or function so far. Well, whenever we have what's called a, let's see, where is the definition, maybe in the next section. No, it's here. On page 410, it's not highlighted, but you have what's called an initial ray and a terminal ray. Okay, it's italicized in your book there. Your initial ray is basically what goes along the x-axis. That's going to be your horizontal, whenever we were talking about our horizontal when we were looking across. Then we have a terminal ray, which in this situation would be an elevation, a line of elevation. Okay? Now, whenever we do this, we can always go out and down and end up making a right triangle. And then we can take information and determine other information based on this. Now, from earlier math courses, do you remember what quadrant this is? 1, very good. So you have 1, you have 2, you have 3, and then you have 4. As far as your quadrants, Roman numerals are what's used. Now what's interesting is as we look at this Cartesian plane, whenever we come up with these points, we are going positive in both the x and y direction. Okay? The x and the y direction. So we're going positive however many units in the x direction and up however many units in the y direction. Now, this same concept, the use of the right triangle, applies with regard to absolute value. Okay? Because remember, absolute value is always some sort of positive distance from 0. We're starting at the origin, so this will be true when it starts from 0, 0, the origin. So what that means is if you have this here, and you have a right triangle, even though that this would be negative in the y direction, like say negative 4 units, 4, this is still a positive 4 units in distance, okay? Just like this, if this was 4, 1, 2, 3, 4, so the length of this side is 4, the length of this side is also 4, it's not negative 4, you don't have negative distance. So we can apply the same concepts, it's just going to be the absolute value of those sides, okay? Because whenever we're using the x and y coordinates to get there. Okay? Does that make sense?
Yeah.
Just like here, even though you're going in the negative x to y direction, it would still be, say, positive 7. It wouldn't be negative 7.
It would be like an absolute value.
Absolute value, yes. Okay? Does everybody understand that concept? Okay, so again, that's really what's important. Now, what happens is, or what we can use is degrees. Here, we may be given certain degrees. So from here, you may be a negative, say, 120 degrees. Well, what would this angle end up being? If you're starting from here going backwards 120 degrees, what will be the angle inside of the triangle there? 60. Very good, because we know a straight line is 180 degrees, so we know that this angle is 60 degrees, and we can use that to determine the rest of our information. Okay? Does it make sense? Everybody follow along, or we still kind of lost? Because this is kind of visually tricky, which can throw our brains a little bit. Cool. If everybody's on board, then that is all I really want to address with that. All right, let's go to 10.5. 10.5, now we're going to talk about radians. We've been talking about degrees, now we're going to be talking about radians. And this is kind of a tough spot to do this, and they're combining both sets of information into one chapter, so we kind of have to put the brakes on degrees, especially since we just grasped that. And now we've got to look into a totally different kind of concept. So it's like you have your good brother and your bad brother.
Well.
Oh, that's pretty messed up. And actually, it's kind of the best way to describe it is you have twins. Okay, one does twins. You have one that does one thing one way, and another one does it a different way. Well, what's funny is they still end up doing the same stuff. Okay, and really, there's not one that's bad and one that's good, one that's right and one that's wrong. They just do it differently, and it's a different way of viewing it. Okay. Looking at 10.5, page 418, we're going to look at radians. A radian is the measure of an angle that intercepts the unit circle in an arc 1 unit in length and has its vertex at the center of the circle. Make sense?
Yeah.
So really I don't need to explain anymore, right? We're done with this section?
Yeah.
We're all good?
Yeah.
Yeah. What I want to do is, if you look at page 419. 419, okay? At that top part, if you think of a circle, it goes around 360 degrees. Okay? 360 degrees. The circumference of a circle is 2 times pi times the radius. Okay? Now, with radians, we are dealing with the radius being 1. With the radius being 1. So we have this. Well, let me go over here. We have a circle, and we are always dealing with a circle with a radius of 1. It is 1 measure unit out. Okay? So the circumference equals 2 times pi times the radius. Since the radius is 1, the circumference is going to be 2 times pi. Now what that means to us is when we're looking at a Cartesian plane, from here, okay, this point we go 1 unit out, as it circles all the way around and comes back to this point here, that value is 2 pi. 2 times pi. 1 lap all the way around the track and back to where you started from is 2 pi. Okay? Given that, what is this point right here?
1 pi.
Very good. Pi, or 1 pi. It is halfway around the track. So half of 2 pi is 1 pi. So what about this point here? What would this be? And we'll get to this one too.
1.5 pi.
Very good. 1.5 pi, right?
No.
Very good. Awesome. I'm glad y'all caught that. No. Wait, huh? And what? So what is it? If it's, you start off, now one thing to consider is the starting point is 0. Okay? 1 lap around is 2 pi. This is 1 pi, so what is this?
You just half a pi or just t.
What's that?
Half a pi or just t.
Just t?
Yeah.
So it's not a full pi, it's, do y'all get that?
Yeah.
I got
So
it.
you have
Oh,
pi,
wait, now I got it.
and you cut it in half, it's just 1 t, that's pretty clever, yeah. So this is 1/2 pi. So if we're starting at 0, this is 1, well this is half of 1, 1/2 pi. What is this one down here? Well, it's going to be 3/4 pi.
Yeah.
Right or wrong?
I don't think
I
Wrong.
don't think it's right.
Why don't you think it's right?
Because, yeah, 1/2, 1.5 essentially, or,
Mhm. Very good. How can this be 3/4 if this is 1? And we're past 1 already.
Right.
So, and this is something that visually throws people with radians here. You're thinking 2 pi, 1 pi, well this is half pi, well this is 3/4 the way around the circle, so this has to be 3/4 pi. That actually is not correct. It can't be 3/4 pi because this would actually be 3/4 pi. So from here, what would this be? If this is 1 pi, this is 2 pi, what is this?
1.5 pi.
Right. What's another way of saying that? So 1.5 pi, what's another way of saying that? 1 and 1/2, or what's a ratio? Or a fraction, sorry. What would be a fraction to put down?
3 over 1. Wait, no.
2? No.
What's the fraction for 1.5? An improper fraction, what's that? Okay, do this, 1 and 1/2. Make this an improper fraction. Means the number on top is bigger than the number on bottom.
Here, 2.
3/2, very good. 3/2 pi. Or you can say 1.5 pi, 1.5 pi. Okay, so this is the biggest, most difficult thing to get past. Once you get past this and you understand this, then the rest of this section becomes much more simpler and easier to grasp. Okay, so you start off with 0, half pi, pi, 1.5 pi, or 3/2, and then you're back to 2 pi. And then you start over. This doesn't get bigger and bigger and bigger, it just starts over. Okay? Think of it as one track, and you do one full lap is one set. Okay? Then you start over, do another lap again. Okay? Now, with that, if we were told to now, okay, let me ask you this. So from this point to this point is how many degrees?
Well, it's 160, no, 260.
What's a line?
Oh, 100.
180 degrees. So one halfway around is 180 degrees. Okay? Which equals pi for radians. Okay? Here we're doing radians, and that's whenever we incorporate pi. Degrees, we have the little degree sign up top. Okay? So, if we have the ratio of this would be, I'm starting to make the board look messy here. So, 1 pi radian per 180 degrees. Okay? If you want to think about this being a full circle, well, that's going to be 2 pi radian over 360 degrees. But what happens is we're simplifying because there's a 2 in both of these, and we end up back here. So your standard ratio is going to be 1 pi radian for every 180 degrees. Does that make sense? So then we can use this ratio to figure out missing information if we want to translate or change something over. For instance, we are given pi over 2. Change this to degrees. Well, whenever we do our any type of translations, like from milliliters to liters and so on, we always have to have it set up to where they cancel each other out and we figure out what's left over. Well, here we know that 180 degrees is 1 pi, right? Okay, does that make sense? So then your pi's cancel out. 180 degrees divided by 2 equals 90, and what's left over are degrees.
That's it.
And that's it. So pi over 2 is simply 90 degrees. Which, think about it. If you have 1/2 pi and 1/2 times pi, or pi over 1, equals pi over 2, it's the same thing as 1/2 pi. So pi over 2 is simply going to be 90 degrees. The distance from here up here in degrees is 90 degrees. Does that make sense? So all we're doing is translating. Pay attention to this, use this. If we had 3 pi over 4, 3 pi over 4, change that to degrees. Well, we're still going to put pi on the bottom, 180 degrees up top. Okay, well 4 can actually go in, or our pi's cancel out. 4 can go into 180 45 times. And so 3 times 45 is 135 degrees. So 3 over 4 pi is 135 degrees. So use this, make sure that it can cancel each other out. And you can even go back and forth. If you started off with 135 degrees, well, 135 degrees times, pi over 180 degrees. Well, then whatever you're left over with will be with pi, which is actually 3 over 4 pi. So that's how you can translate or transfer degrees into radians and radians back into degrees. Now what's interesting, everybody do this real quick. And we're running out of time here. But take your calculators. And what is, let's see, take all right, so we're in degrees. Now go to radian and do 3 divided by 4 equals, and multiply that times pi. Equals 2.356.
Can you repeat real fast what we're supposed to do? I messed it up.
What was it?
Think so.
Where are we? 135. Okay, you know what? Let's back up a little bit. Well, what I'm wanting to do is compare the 135 degrees with the 3/4 pi. Okay? Now, what you can do is compare this on your chart. If you go to radians, you go to your radian selection, 3 divided by 4, and then multiply that times pi, what do you get?
2.35, but round that up, so 2.36.
Okay, so 2.36. Now, whenever you looked at your table, what was the highest What was the highest degree that it went up to? 90. So here we pose a problem. We have 135 degrees.
No.
So what do we do?
We multiply till we get that number.
Do we?
No.
Burn our math book.
Yes, burn the math book and that's where you get to it.
I'll supply the matches and the fire pit. Everything else.
Don't bring the books. Don't bring the books.
So if you look at, I lost my place because, so 135 degrees gets you here. This gets you to 135 degrees. What's left over from the 180? So basically what you're looking for is this angle right here,
45.
45. Okay, now let's go to our table and let's look up 45.
Oh yeah.
Okay,
Oh. Okay.
now this is going to be, let's do this. You're in radian mode. Okay, now we have 2.36 and take the sine of that. 0.7071, right?
Yeah.
Now take the sine of 45 degrees, or look at, in degree mode, you take the sine of 45 degrees, what do you end up with? You can look at your table to reference it if you want to.
45.
But here, your 45 degrees, what's the sine of that?
0.7.
Yeah, 0.7071, which is what we came up with in radian mode. Does that make sense, what we just did? Huh?
No, I got it.
Okay, so now we're still getting there to the same place, it's just different methods. It's kind of like going over to England and doing the, like there is no Big Mac, I'm sorry, there's no quarter pounder over in Europe at the McDonald's, but there is here in the United States because of the measurement that we use, right? This is the same thing. You can use radians or you can use degrees and still come up with the same measurements. Okay, it just depends on what you're asked to do or what it is you're trying to accomplish. All right, finally, real quickly, I want to do one more section. And I'm actually going to tie in these two. If you were to break this circle, okay, let me erase all of this. In fact, I'm going to rewrite it, just so it makes more sense. If you were to take this circle here, okay, you have 2 pi, pi over 2, pi, and then 3/4 pi, right? No.
No.
3 pi over 2. Thank you. Now, if you were to break this up into a wavelength, okay, where you took this circle and it turned into a wavelength, okay, and you went up and down and back up, one full wavelength, half of the circle here is pi. You've made it halfway through the wavelength, and think of it as half of that circle. You haven't made it all the way around the track. One full complete wavelength is one lap around that track, or one travel through that path, okay? And then you got to stop and start all over. So the ending is going to be 2 pi. Here we start at 0, half the wavelength is pi, the other half gets us to 2 pi. If we were to break these apart, essentially you could put them together and it wouldn't be a complete circle, it would be an oval, but it would be the same as one lap around, okay? So likewise, half of the way to here is going to be pi over 2. And then here it's half or 3/4 of the way is going to be 3 over 2 pi. Okay? So again, if you think of it in terms of a circle, and you were to break it up, here we're going around a track this way. Well, here we're going to look at wavelengths. So one complete wavelength is to where you start on the x-axis, you've made one trip up and one trip down, and you're back on the x-axis. You always have to go up and down, a positive and negative to equal out to a 0. Okay? And you'll end up at 2 pi. Now, there are different frequencies to where these wavelengths will be either more rapid or they'll be more drawn out. Regardless, there is only one wavelength, and that's whenever you start from one point and end up in that same point after having gone completely up and below it, and you're back to that same axis. Now, with that, you have two more definitions that I want to go over. And I'm trying to find, okay. On 10.7, page 430, you have what's called the amplitude. The amplitude. 1/2 of the distance from its highest to its lowest point. 1/2 the distance from its highest to its lowest point is called the amplitude. Okay.
So I gotta find it somewhere.
Gotta be somewhere.
All right. And then finally, you have what's called the period. Okay? The period of the function. So this is going to be the actual length of the entire wavelength. So you have your amplitude, and then you have your period. Again, amplitude is 1/2 the distance from the highest to the lowest point, and then the period is the length of the wavelength. Okay, the length of it. Alrighty. Now that will be all for right now. Whenever we will go, 10.7 can be a little confusing. Okay, it goes over this so briefly during this course that as long as you're getting what we've talked about here, where with degrees versus radians, that is the important part of this. If you end up going into physics and other areas of either mathematics or science with regard to frequencies and wavelengths and things like that, that's where you're going to get into this more deeply. So I want exposure from this, or to this, but we're not going to go into crazy detail about it. Okay? It's more just exposure. That will be all. Thank you very much.